Hello, hello! Welcome back to PreCalc. Today we're going to be talking about radical expression skills. So grab those notes, put away the distractions, and let's get going. We're going to start off by defining our radical expressions. So radicals are a way to kind of undo exponents. We have a lot of ways to undo things in mathematics. We don't like being able to do something without being able to undo it. So addition, we come up with subtraction, multiplication, there's division. Exponents have radicals. So square root, cube root, fourth root, fifth root, these are all radicals. The number that goes inside them is called the radicand. For example, the cube root of 27 is asking, what number do I cube to get 27? So I also have this handy dandy chart that has all of the perfect squares, perfect cubes, perfect fourths. If you want to like quick screenshot this or something so that you can reference it later, or pause the video and fill in the table at the top of your notes, that works too. But there it is. There's all that information, going once, going twice, sold. Moving on to simplifying radicals. So in order to simplify radicals, we have to pay attention to the number that's outside of the thing. So, you know, to this number out here. You need that many of a thing to pull out of the radical. And what? So we're going to be finding the prime factorization of the radicand, the number inside, and then we're going to be looking for groups of that many, that the outside thing, and then pulling them out in groups. I'm looking for groups of the same factor. So that's like poorly written, but that's like math speak version. My personal thing is I like to tell a story. You're inside of a haunted house. In order to escape, if it's a square root, you have to find twins, and one of the twins will die so the other one can escape. If you're inside of a cube root house, you're looking for triplets. Two of the triplets will die, one will escape. If you're in a fourth root house, you're looking for quadruplets. Again, three of them will die so that the one may escape. And that's kind of how it is. Little, not exactly, PC friendly, but it helps me remember. So, but these all start with finding the prime factorization. And what better way to find a prime factorization than to do one of those glorious factor trees? So we have 2, so this becomes a 1, a 2, a 6, another 2, 1, 2, 6 becomes 6, 3, 3, so that becomes 21, 3, and that's a 7. I'm looking for pairs or twins. So here's one set of twins, and here's another set of twins. One of them is going to die so that the other one can escape. The 7 does not have a twin, so he is stuck inside the haunted house forever. And this simplifies down to 6 root 7. Fourth root. So again, we're going to be going with our factor tree bonanza. And 2 becomes 24. 2, that would be a 12, which becomes a 6, which becomes a 3. So I do have one grouping of 4, so something is going to escape out of this house. It's a group of 4 2s. So we're going to have a 2 on the outside, and the 3 is stuck inside forever. Don't forget to put the 4 right there, otherwise it's not a fourth root, it's a square root. Derp. Cube root. Notice this guy has a negative. Cube roots can have negatives on the inside. Square roots, fourth roots, any type of even root, you should not be seeing a negative inside there yet. Wait until next lesson. Then we'll talk about that. But for right now, there shouldn't be a negative inside there. So I definitely know that we're going to be pulling a negative out, because you can have, anytime you see a negative, you just need an odd group of negatives. So you can have -1, -1, -1. That would give me a negative sign inside of a root. I can have 5 negatives if that's how many I need, or 7 negatives, however many that it is that I need in order to pull the negative to the outside of the radical. So I'm just going to start by pulling the negative outside of the radical, because he's distracting, and I don't really want to deal with him being distracting. Okay. Oh my goodness, there's variables this time. All right, so 162. Did we do 162? No, we had 126. Bummer. All right, 2, which turns into 81. 81 is a 3, or technically a 9, but 9 times 9 is really, 9s are made up of 3s, so I'm going to pull out 3s, because I want the prime factorization. And we do have a group of 3 3s. Hey, come here. Shoop. And so that means right now I can pull out a -3 out of my cube root. I'm left with 2 times 3, which is 6, m to the 6, n to the 9. Okay, so this bit I'm actually going to list them out. So, you ready for this? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. And groups of 3. 1 group of 3, 2 groups of 3. So that's going to become m squared. And then a group of 3, a group of 3, a group of 3. So this is n cubed. So I'm going to have negative 3m squared n cubed cube root of 6. Was there an easier way to do that? Yes, there was. Okay. Adding and subtracting radical expressions. So the first thing you always do whenever you're doing other things with radicals, you always want to simplify the radical first, because maybe you don't have a radical. Maybe it just looks like you have a radical. You don't actually have to do anything with the radical. So we always simplify them first, just because it just makes, sometimes things don't look like they're similar, but they are, and it just makes things going forward easier. So always start by simplifying the radical. After we simplify the radical, we go looking for like terms. Now, like terms with radicals are a little bit weird. You're looking for the same type of house and the same number in the house. So I need a square root 3 and a square root 3, like that first example there. Those guys, they're totally like terms. Totally like terms. So I can treat them, I can just basically pretend like they're a variable, like x, and I'm going to write it again, the square root 3, and then I'm going to add the numbers in front. Remember, if there's no number, there's always a 1. And so this is 1 plus 2, which is going to give me 3 root 3. My next example, I don't have the same type of house. This guy is a square root, and the other one is a cube root. So I can't actually combine these because they're not the same type of house or the same type of root. Can't combine. And over here, I have a 3 inside one and a 2 inside the other. Again, I can't combine because I don't have the same type of ghost inside or the same type of radicand. No touchy, the last two. But I can do something with the first one, which is why we always simplify first. So we're going to start off with 32 and 50. So 32, 2, which is 16, 2, which is 8, 2, which is 4, and 2 and 2. And then 50, 2, which gives me 25, 5, and 5. We go looking for twinsies. So that's 2 times 2, or negative 5, which was already there. Negative 5. And then we have times 2, and then square root the 2 because he didn't escape. And then we have plus 7 times 5 because they escaped. Times 5, and then the 2 is stuck inside forever. Do not pass go, do not collect $200. So this becomes negative 20 square root 2 plus 35 square root 2. I check my houses. I have the same type of house, and I have the same prisoner inside. So these guys are like terms. I can combine them. And that's going to give me negative 20 plus 35 would be a positive 15 square root 2. Okay. I'm going to do the next one. I'm not going to do the third one. I don't think. Hang on a second. Let me check and see if it comes out to something useful. Nope. I'm going to do the other one. That one works pretty much the same way as the one that we just did. But I'm going to go ahead and do this other guy just to show you what different houses can sometimes look like. So 24 is 2, 12, 2, 6, 2, 3. And then 12 is 2, 6, 2, 3. And then, did we already do 54? I don't think we actually did 54. So we get to do that one. Yay, 2, 27, 3. 9 and 3, which is 3. Looking for my escapees, a pair of 2s, a pair of 2s, and a pair of 3s. Alrighty, so let's write these guys up. This one becomes 2 times 2, the escapee, square root of 6. This guy minus 8 times 2, the escapees, the 3 stuck inside. and then plus 7 times 3, and the people that did not escape are 2 and 3. 2 times 3 is 6. All right, so let's clean up our numerators. 4 root 6 minus 16 root 3 plus 21 root 6. Our numerators? That was not the right word. Our coefficients? Yes, clean up the coefficients. So 21, 4, that gives me 25 root 6 minus 16 root 3. And that, my dears, is my final answer for adding and subtracting radicals. Multiplying radicals. We just multiply them. Distribute. The main thing to remember is that the things on the outside of the haunted house can mess with each other. The things on the inside of the haunted house can mess with each other. They cannot mess with inside-outside. Prisoners can play with prisoners. Escapees can play with escapees, but prisoners can't play with escapees, or vice versa. Like, it's like they're in like a parallel dimension and they can't actually interact with each other or something. However, whatever story in your brain helps you remember that. So I can do 3 and 4. They can impact each other because they're both outside of the radical. So that gives me 12 root 2. 3 and 2, those guys are both on the inside, so they can impact each other, and that's going to end up with a root 6 and a 4 on the outside. The square root 3, because of the plus sign, we're going to end up doing distribution, because this is a binomial. There are 2 terms here, not just 1, but 2. So we're going to do 4 times the square root of 3, plus the square root of 3 times the square root of 2. So we're going to leave this as 4 root 3, and then we're going to add plus root 6. Why do we always put the number on the outside instead of, like, the outside number always goes first instead of second? Why do we do that? So our process, we simplify all the radicals, and then we combine like terms. Multiply, simplify, combine. There we go. So let's get to it. Multiply. So things on the outside, the negative and the 2 go together. Times 18 times 20. Ugh. I really don't want to factor tree 360. I really don't want to do that. So I'm going to change up my order of directions. I'm going to do that first. That would be a 2, which is a 9, 3, and 3. Those guys escape. Negative 3 root 2. Oh, that's so much cleaner. So that's our first one. And then we're going to multiply that by 20, 2 and 10, which is 2 and 5. There we go. So 2 times 2 root 5. So this is negative 3 root 2 times 4 root 5. That's cleaner. Negative 12 root 10. And that is not simplifiable, so we'll move on with life. Probably should have multiplied them first, but you can also simplify them first and then multiply them and then simplify them again. And then look for like terms. Whew. All right. Bippity boppity boo. We've got square root of 18 minus ick. Yeah, minus ick. I like that. Minus ick. Let's hold up here. I don't want to make this number bigger. I'm so tired of these factor tree ladder thingy-ma-choppers. 2, which is 6. 2, which is 3. These guys can escape, so that's square root 3, square root 6, minus 2, square root 6. Oh, well, hold up. That stuff inside the parentheses? Those are like terms. I can combine them. Bleep that. That would become negative square root 6. All right? Because it's a 1 minus 2. Yeah. So then this gives me negative square root 18. And I can factor tree that. 18, which is 3, 9, 3, 2, whatever. And I can pull that out negative 3 square root 2. Oh, that was so much nicer than doing it the other way. Can you do it the other way? Totally, 100%, perfectly fine to do the multiplication and then do the simplification. I just don't like making big trees. So, oh well. Oh, dividing radical expressions. Cannot leave radicals in the denominator. Yeah, unfortunately, you can't do that. Radicals in the denominator, it's considered poor taste in math. It would be like writing a giant run-on sentence in English, or not capitalizing any letters, or not putting spaces in between words. It's just not done. Can people still understand what you wrote? Maybe, but we don't do it. The reason we don't do it, it's a long history lesson. Basically, way back before calculators, there was this tool that we called a slide rule. And slide rules it was hard to deal with radicals in the denominator on a slide rule. It was easier to deal with them in the numerator, and it's not that hard to move it from the denominator to the numerator. So it just kind of became standard mathematical practice to always put the radicals in the numerator instead of the denominator. Slide rules have gone extinct. They're very extinct, and yet we still do this thing to this day. Lucky us. All right, so there's two cases of when you can have a radical in the denominator. Maybe you have a maybe you have a monomial as your denominator, meaning there's no pluses or minuses. If possible, create one radical of the numerator denominator and simplify the radical. Maybe the denominator part will go away. You know, maybe you can just like cancel things out. What that means is doing like a square root of like 4 over 2, something like that, and then you can simplify things down and the denominator will just go away. If not, you'll have to multiply the numerator and the denominator by the radical that's in the denominator, in the denom, and then simplify. If you have a binomial denominator, we'll talk about that one when we talk about that other example. But for starters, let's talk about the monomial ones. So this 6 over 2, let's make a ginormous denominator and hope that things cancel. Does 480 divide by 6? 48 divided by 6, so 480, would stand to reason, does as well. 6 over 2 turns into 3. 48 divided by 6 is 8, so that would become 80. We can't leave it there, though. We do need to actually simplify this guy the whole way, so yay! I'm going to do a factor tree this time because I'm tired of ladders. 2 and 4, 2 and 2, 2 and 5. Ladder's a little bit nicer because it makes it easier to spot your pairs and you don't end up doing that randomness, and you don't forget to put the 5 on the inside. 2 times 2 times 3, 4 times 3 is 12. Boom. Okay, that was beautiful. It's not going to work on the next one. It's just not going to work. It's just not going to do it. 8 and 3, you can't divide 8 by 3. No! Okay, so this time we're actually going to have to do like our rationalizing thing. And what we're going to do is we're going to multiply the top and the bottom by the square root of 3. I can always multiply a fraction by 1, and any number over itself is 1. So I can do this. Totally legit. This becomes 6 square root 24 over 4 square root 9. But the square root of 9, that's one of my perfect squares, and that becomes 3. And so this is 6 square root 24 over 12. 6 and 12, those cancel out. I end up with 24 over 6. Yes. No. 2. Yes. Yes. And then we do our factor thingamajobber. 2, 12, 2, 6, 2, 3. Swoopy. 2 root 6 over 2. But now the 2's cancel, and I'm just left with square root 6. Whew. Okay. That wasn't terrible. Okay. Binomial denominator. Okay, new thing, new directions. You cannot make one radical out of the numerator and the denominator. If you've got a square root on the top and you've got a square root on the bottom and there's a plus or minus on the bottom, you can't do the square root simplifiable thing that we did in the first one. That's what that pink stuff says. We're going to need to multiply the numerator and the denominator by the conjugate of the denominator. Mrs. Norton, what is a conjugate? So glad you asked. So if we had a plus square root b as the original, the conjugate is all the same pieces, but you change the sign, you make it a minus. So basically what a conjugate does is it changes the sign in front of the root, or in front of the radical. That's the sign we have to change. We can't change the sign in front of the real number, or the non-radical number, the non-radical number, because then it doesn't actually do what we're trying to do. We're trying to get rid of the square in the denominator. So my conjugate for this 1 minus root 5 is negative 1 plus root 5. Floop, floop. Negative 1 plus root 5. And that's going to give me 4 times negative 1 plus root 5 over negative 1 minus square root of 5 times negative 1 plus square root of 5. There we go. So that's negative 4 plus 20 over positive 1 minus square root 5 plus square root 5 minus square root 25. Let's see, top turns into 16. 1 minus square root of 25 would be just 5. These guys in the middle, they cancel each other out. That's exactly precisely what we want to happen. We want the radicals or the roots to cancel each other out. So then that's gives me 16 over negative 4. 16 divided by negative 4 is just negative 4. And we're done. Yay. Oh no. There's one more thing to go through. Radicals written as exponents. So radicals written as exponents, basically they get written as fractional exponents. The denominator of your fractional exponent is the number that goes inside the radical, inside the house. So if you have like, let's do some examples. This p of 9 over 2, this is the number that goes here. Square roots, we don't usually write them down like that. And then we have this guy becomes p to the 9th. And that's that. All of these guys on our next one have a denominator of 3. So we're going to put them inside of a cube root. And we're going to put a 27, an r to the 17, and an s to the 8. But then we have to simplify it, and that's actually a little backwards because now we have to figure out, okay, well, how many times does 3 go into 17 and pull them out? So we kind of jumped the gun on that one. So I'm going to backtrack a little bit. R 17 over 3. That's 17 R's, and I'm wanting them in groupings of 3. I can pull out 5 groupings because that's 15. So R to the 15 is what can come out, and R to the 2 is what's left inside my scary box thing. S to the 8 over 3. That would be the same as S to the 6, 6 over 3. S to the 2 over 3. 6 over 3, that becomes S squared. And S to the 2/3, that guy gets stuck inside there. And the 27 to the 1/3 power, that's actually one of my perfect cubes. So I can't actually pull that one out. That becomes 3 r to the 15 s squared cube root r squared s squared. And just kind of to show the r all the way out. I know I'm kind of like talking in circles. Sorry. That would be r to the 15/3, r to the 2/3. 15/3 is r to the 5th, so that can get pulled out. And r to the 2/3 cannot. Whew. All right, going back the other direction, you basically take the guy out here, and that becomes the denominator, and that's how you do that. 5k cubed to the 1/4. You can split it up some if you want to, so 5 to the 1/4, k to the 3/4. Or you can do, the next one is 4 to the 1/2, y to the 3/2. The square root of 4 is 2, so 2y to the 3/2. That is looking like a 3, not a 2. There we go. Boopity boop. Boop, buddy boop. All right, last but not least, if you're wanting to simplify these guys and write them in simplest radical form, basically what we're going to do is we're going to treat them like regular exponents. So for multiplying the bases, we're going to add the exponents. 3/4 plus 5/2. Fractions need a common denominator. So this is g to the 3/4 plus 10 over 4. So that becomes g to the 13 over 4. Boop. And then this guy over here, 16 to the 1/2 a 6 over 2. Oh, wait, we're supposed to write answers in simplest radical form. Hang on, back it up. Not done with this guy. G to the 13, nope, let's split it up. G 12 over 4, I almost did it again. G to the 1 over 4, so this becomes g cubed. G to the 1 over 4, so g cubed 4th root g. Now I can move on. I forgot to write my answer in simplest radical form. And then b 3 over 2. So 16 to the 1/2 is 4. A cubed. This is going to be b to the 2 over 2, b to the 1 over 2. So 4a cubed b and 1b stuck inside the house. Boom. We made it! It's only 26 minutes long. You know, whatever. Things to remember, the things inside the radical can't touch the things on the outside, and vice versa. We kind of talked about that, just want to make sure that that really drives home. And our next video is going to be about complex numbers. It's a slight detour. Kind of think of it as radicals day 2. What do we do with the negatives inside of an even radical? Oh my goodness, it's going to be great. And don't forget to go and do the video reflection. And happy mathing!